go. Hello, this is AlphaX Team 37, and this is the Papia lander presentation. Next slide. All right, here is our team. Sorry with me, I'm Joshua McCall. I go to California Lutheran University, and I'm a computer science major. We'll start with Alfonso. Alfonso?
Yeah, so my name is Alfonso Mares. I'm a mechanical engineering major at California State University, Los Angeles.
Hi, my name is Jamie. I am a mechanical engineering student at Pasadena City College.
Hi, I am Mohammed Tawfiq, majoring in electrical engineering at California State University, Northridge.
Hi, I'm Gardeni Mejia, and I am a biology major at Pasadena City College.
I'm Jonathan. I'm an aerospace engineering major at Pasadena City College.
I'm Supreeti, and I'm a mechanical engineering major at UCLA.
Hi, my name is Neve, and I'm a mechanical engineering student at Cypress College.
Hi, my name is Alvaro Betian, and I'm a computer science and math major at Pasadena City College.
Hi, and I'm Andres Castillo, and I study electrical engineering at California State University of Northridge.
Awesome. This is our team. So here is a breakdown of all of our positions and duties. Next slide. And here is our breakdown of our major milestones, starting with A and B, which allows us to study the planet and also create our PDR. Phases C and D goes into the design process, and phase E goes into the lander operations when we're on Enceladus. Next slide.
For the mission statement, the primary goal of this mission is to determine the composition of the ocean on Enceladus by analyzing the plume material released at the Tiger stripes, investigate geochemical activity for signs of life, mainly looking for energy, detect any presence of organic and inorganic compounds in the plumes, which will be achieved by using the MOMA, and understand the cause of the plumes and the composition of the ocean. Understand the local geography by using the MASCAM-Z, which will help us have a better understanding of the geographical of the surface.
In order for a mission to be successful, the Mars Organic Molecule Analyzer must be able to detect a mass range of 50 micrograms to 500 micrograms and plus minus 0.4 micrograms. It also must collect at least 1 milligram of plume material per day. The MASCAM-Z must be able to collect 75 microradians per pixel for the zoom lens and 3 milliradians per pixel for the wide angle lens. Next slide.
For the scientific objectives, the first one is understand the composition of the Tiger stripe plume material, and understand the geochemical activity of Enceladus. And by using the MOMA, we will be able to detect presence of organic and inorganic compounds, as well as analyze high molecular weight compounds, which are vital to determine whether there could be life on Enceladus. And finally, use the MASCAM-Z to take 3D pictures of the landscape around the lander. The MASCAM-Z possesses different wavelength information that can reveal minerals deposited in the ice on Enceladus. Next slide.
And for our instrument payload, as Gardini mentioned, we have a panoramic camera, but the most important instrument is the Mars Organic Molecular Analyzer, or the MOMA. It has dimensions of 14 by 12 by 20 centimeters. There will be a funnel at the top of the instrument to collect plume, and a motor will power a drill that will allow for easy flow of the plume through the funnel onto the MOMA. Next slide.
Two sexiest factors of our frame are its weight and rigidity, made from a composite material with carbon-based layers of fiber, woven and glued into a fabric. Papia frame material is lighter than aluminum and more rigid than steel, and not only strong but also highly stiff, that ensure the engine's vibrations do not damage the payload. We use a sandwich design. Two extremely thin sheets are glued on both sides of a foam core. All compartments are held inside with bolts and special nuts, while outside, 30 layers of foil, switching between polyimide and mesh, will insulate and protect the lander from the environment. Next slide.
For the electrical components, we have the RADs and IMUs, the IMU, MMRTG, RAD 750, and the low gain antenna. The IMU provides 3 axis information on its position. For the MMRTG, it has been proven to produce heat and electricity under harsh conditions encountered in deep space for decades without any maintenance. And as for the RAD 750, the RAD 750 is basically the brains of the rover. It uses VxWorks, and there will be 2 identical RAD 750s in the rover. It operates at up to 200 megahertz speed and has 2 gigabytes of flash memory. Last but not least, the low gain antenna. We will be using the low gain antenna to send and receive information to and from Earth. Now, Jamie.
To help with orientation of our lander as it approaches descent and landing, we are going to depend on 4 MRM106F thrusters, 4 MR106L thrusters that will work together, and we are going to have 4 snowshoes at the bottom of our lander that will be powered with hydraulics that will help the lander land gently and safely on the surface of the moon. Next slide.
So as soon as we enter the atmosphere, it's going to be at about 287 kilometers. As you can see, the lander is nice and closed up, and that's the perigee. So after it gets to about like 200 kilometers at about like 125 meters per second, the thrusters are going to fire and the deceleration is going to begin. And when it approaches 1800 meters, the LiDAR and legs will deploy. And last, it's going to, once it gets to 20 meters, at about like a 0 to 10 meters per second, it's just going to stop, turn thrusters off, and go into free fall. Now we're going to move on to the next slide.
For our landing site, we use various Cassini data to verify our site. We use image data to locate the lander in the south polar region, which is close to the tiger stripes. We use infrared data to ensure the lander is within the high plume density area, and we use topography data to ensure the landing site is relatively flat for safe landing. Next slide.
In terms of scientific value, unlike Cassini, which is only able to sample the lighter and faster molecules that escape the surface, this mission would be able to sample and collect the heavy molecules that fell back to the surface in order to create a more holistic picture of Enceladus and determine if the ingredients for life are present. Also taking close-up images of the surface would help with having images for future missions to Enceladus, as well as have context for scientific research. Next slide.
As for the assembly and testing of the lander, we will be broken up in 3 phases. In phase 1, we'll test each instrument individually. In phase 2, we will test the lander as a whole when it's built. And phase 3, we will start testing the lander in severe weather conditions to model the Enceladus environment. Specifically, we'll be looking at the Mars Organic Molecule Analyzer to ensure that it's functioning at 100% expectancy. Next slide. Starting with the risk matrix, which is on the left-hand side, this will show the likelihood of the consequence based on scores on being too close to the geysers on Enceladus. Now on the right-hand side, we have the F and EA diagram, which shows all primary and subsystems and how they could fail during the mission. Next slide.
Some of the major environmental concerns are not having enough light for imaging, as well as extremely low surface temperatures, which will be mitigated by having our mission arrive at 2035 when Enceladus is having its southern summer. So there will be more light and warmer temperatures. There will still need to be internal regulation to ensure instruments are within their operating temperature ranges. And in terms of visibility, the lander will reach the surface when Enceladus is closest to Saturn, as there will be less plume material released. And the experiment will commence when Enceladus is farthest from Saturn, as there will be more plume material released to be able to collect samples and to prevent surface contamination that might alter the experimental results. the last stage of the EDL procedure will have the thrusters turned off. Next slide.
All right, so how do we plan to outreach the community? So we plan to make partnerships with organizations such as the Society of Hispanic Professional Engineers, and we also plan to make small workshops for kindergarten to 12th grade to introduce them to the STEM field and such as robotics and astronomy, and also to inform them about our plan of Enceladus. Next slide.
Okay, so for our budget, we started out with rough estimates that we sourced based on previous NASA missions documentations. And then as we got more and more data from the engineering and science departments, we adjusted the budget to fill our needs. And a lot of the stuff we couldn't really find on Google, so we used documentation of instruments that were sort of tangentially related to the instruments that we needed. And we accounted for a 20% error margin as part of the budget because a lot of the manufacturing costs weren't really concrete. And then next it's going to be Joshua with the evolution of the project.
Awesome. Now for the science department, we had two major evolutions. The first iteration was scooping the ice from the ground or any icy material from the ground. But then we thought something was better if we just make a cone that can collect the icy samples that come from the tiger stripes or geysers on Enceladus. Next slide.
Cool. Now on the engineering side, it started off with we got to a lander that is able to open and close, and this allowed for us to integrate the payloads more, as well as the electronics, such as the master cam and the funnel and the MOMA, electronics, the low gain antenna, as well as the EDL. So the snowshoes and the LiDAR were able to come out and be implemented. And now I'm going to, next slide.
Awesome. So this is to conclude our presentation of the Papia lander. We hope you learned how our PDR sequence is going and how our designs iterated from the beginning to the end. Thank you so much for my team, and thank you so much for watching.